Hi there, ladies and gents. Dr. Skinner here. Welcome to Chapter 3 of the Administration of a Computer-Based Information System class. And today we are going to be talking about infrastructure. In more detail, managing the information systems infrastructure and services. We have 4 learning objectives today. Describe how changes in the business's competitive landscape influence changing infrastructure needs. Describe the essential components of an organization's infrastructure. Look at some of the managerial issues associated with managing infrastructure. And we're going to touch on cloud computing and other trends that can help an organization address infrastructure-related challenges. So to the first one, describe how changes in a business's competitive landscape influence changing infrastructure needs. So most people, when they live in a city, expect basic municipal services that are actually invisible to them. We take them for granted. So we can see them, for instance, in this kind of context here. We can see provision of water, roads, well, probably not with the potholes being seen here in Houston, light and energy, and electricity. Okay, so these are all the different infrastructure components that we expect. Okay, cities with good infrastructure are considered more livable in than others, and they're also probably more attractive to business. So when we talk about infrastructure, we're talking about these structures that enable the provision of services. So in the same way that we expect water and roads and lights and electricity, having these structures, they enable the provision of services as a result. So organizations, when they think about organizations in the city, they choose site locations based on these, don't they? I give you the example of a data center close to an internet backbone and located nearby cold water for energy and cooling purposes. And that's what Google did in Finland. They kind of located a new data center close to an old paper mill and near a backbone, and it gave them exactly what they wanted. Okay, so infrastructure components of a city enable the provision of basic services. Even as countries and societies depend on an infrastructure of roads and power and communication to function, businesses depend on their information systems infrastructure to support their organizational and value creation processes. So without a solid IS infrastructure, many businesses are left with unreliable support, and business processes will be subject to interruption, delay, and failure. Just remember what we talk about when we say business processes. Earlier on, we defined business processes as the activities organizations perform to reach their business goals. It includes core activities that transform inputs and produce outputs, and supporting activities that enable the core activities to take place. So to enable such processes, I can't say that word, processes, organizations rely on 3 basic capabilities: processing, storage, and transmission of data. So we think about the interaction between business processes and applications and databases. All the things that go on are on top of the infrastructure world. So infrastructure is critical. So application software, the top level underneath business processes, these are the software tools used to complete the work required to operate and manage an organization. We're helping business processes. Think about accountants going from thick ledgers, these thick books, updating all their notes, to software that automates. These in turn sit on and utilize databases. So databases are the collections of data that our applications will typically reference. Everything resides on infrastructure. Okay, everything resides on infrastructure. So infrastructure is key. I've got to say, ladies and gents, infrastructure is not sexy. All right. If you're working in an investment bank and you're working in the infrastructure world, or you're working on trading applications, if you're in the infrastructure world, you're tucked away in a little office somewhere in the suburbia where it's very boring and not much going on. And if you're working on trading applications, you're actually sitting on the trading floor, interacting with traders, and it's really, really exciting. And you're in the face of people who are making big decisions, and they rely on you. So there's a kind of a downside and an upside to actually working, it's just a kind of bit of a tangent, between working in an application space and working in an infrastructure place. And I actually worked in both, and I faced off from the infrastructure side, facing off to an application team, and then I moved to that application team and faced back to the infrastructure side. And it's very, very different component parts. So what are the component parts, speaking of which, of an organization's IS infrastructure? And there are 5: hardware, system software, storage, networking, and data centers. Let's look at these in turn, starting with hardware. There are many different levels of hardware, going from the largest down, and you can see them on the screen. We start off with supercomputers, which are used to solve the most computationally demanding problems, such as weather forecasting or scientific research. Very, very, very expensive. And I use one. We'll talk about that in a little bit. Mainframe computers used by businesses to help enterprise applications and perform transaction processing. So these are the main central computing systems for large corporations. Mission critical, doing things like transactional processing, really, really important to the organization. Servers that host content and information for online access and retrieval. Workstations are powerful computers typically used by one individual for demanding applications such as graphical design or engineering simulation. These are different to personal computers. That they are also used by one individual, but they're used by normal computer users to facilitate their personal productivity. And then, of course, we have mobile devices, which are used by users on the go with the ability to connect anywhere and at any time. Next part of infrastructure we're interested in is system software. Essentially what we're talking about is operating systems. So it controls the computer hardware operator. So it does more than that, actually. It does more than control the hardware operations. It kind of coordinates the interaction between users, between application software, between hardware, and between peripherals. It provides a common layer for different underlying devices, so that applications only have to be developed for different operating systems rather than for each different computer model. And that makes a lot of sense. So system software makes computers functional. It manages all the aspects of the hardware inside and connected to the computer, and it also coordinates the applications running on the computer. And it's something we typically take for granted. Okay, so the operating system, and I rather like that. It kind of coordinating the interaction between users, application software, hardware, and peripherals. It's something we don't look at it that way typically, but actually it plays a really important part. Next component part, storage. There are 3 categories of data storage with multiple technologies available for each. And typically each of these 3 different categories will have different physical storage technologies being used. The first one is operational. Operational storage is a storage computers access while performing normal processing operations such as data analysis. Backup storage involves copies of operational storage used to recover from things like system-related disasters and so on and so forth. And then archival storage, long-term storage of data that doesn't need to be readily accessible by computer systems. So things for compliance, for reporting, and similar. Efficient storage and retrieval of data is key for organizational success. And that, ladies and gents, is why database is a core class in the MIS degree, because it is so important. The next component part is networking. Computer communication follows the same model as human communication. It just uses different transmission media and protocols or languages. We think about how we interact with people. So we'll see on that diagram on the right. So sender develops and codes the messages and says, how are you? The message is sent and the receiver receives and decodes that message. Okay. So the message needs to be formulated, needs to be encoded, transmitted, received, decoded, and understood for communication to have taken place. Okay. So just imagine if in the bottom one, you're applying for a job in France. Can you decode French? Maintenant, je parle français un petit peu parce que j'étudie le français à l'école pour 8 ans. And I did study French at school for many years. But so I probably can formulate, encode, transmit, receive, decode, and understand communication between French and English. But the majority of people probably cannot. And so we need to have protocols and rules in communication. Okay, so the thing to remember is just that there's a lot of commonality between human communication and computer communication. You need to have a sender and a receiver. You need to have a pathway for the communication to take place on, and you need to have rules and protocols in place for communication to be understood. You need to formulate your message, encode it, transmit it, receive it, decode it, and it to be understood for communication to have taken place. The next level is servers, clients, and peers. So servers provide services. They host applications and content for use by client computers. Client computers, they use servers' services. So client computers consume resources hosted by servers. Peers do both. Peers, P2P, they work together to share applications and data, working as both a host and a client, often at the same time. Here's a question for you. What do you think are the benefits of a peer-to-peer setup, which you might see typically in small offices, versus, say, a server-client environment? I'll give you just 10 seconds to think about that before I give you the answer. Well, typically they're cheaper. All right, so you actually you can almost outsource your server environment to your whole environment. So they're cheaper, they're more flexible, they're easier to grow, and actually they're more difficult to knock out. If you're trying to attack a server to take down a network, you don't actually know where the server is because your peer-to-peer environment shares all the resources across everywhere. And then we come to networks. So networks are typically used to connect devices within an organization or across organizational subunits. Okay. So what do we have? Personal area networks, things like Bluetooth, and wireless communication between devices under 10 meters. LANs, local area networks, sharing data, software applications, other resources between several users, maybe in a building. LANs are becoming wireless, so WLANs or LANs, using high-frequency radio wave technologies. These are also referred to as Wi-Fi networks, which stands for wireless fidelity, which I didn't know, but now you do. Wi-Fi stands for wireless fidelity. These are easy to install as there is no need for cabling. Wide area networks can range from spanning multiple buildings, sometimes called a campus area network, to covering the area of a city, sometimes called a metropolitan area network, to worldwide. The internet. That's a good segue. So the internet is a network of networks connecting many different networks together seamlessly. Okay. The World Wide Web is a way of addressing internet locations, representing data in web browsers, linking sites together with URLs, and all the web content based on these standards. Okay. So a web browser is a software application that can be used to locate and display web pages, e.g. Firefox, Safari, Chrome. HTML stands for Hypertext Markup Language, which is the language understood by web browsers like Google Chrome. HTTP stands for Hypertext Transfer Protocol, which is the communication protocol that web servers use to process requests from web browsers. So HTML, Hypertext Markup Language, language understood by web browsers. HTTP, Hypertext Transfer Protocol, communication protocol that web servers use to process requests from web browsers. URL, this is our URL, Uniform Resource Locator, used to identify and locate a particular web page. Where's my notes? An URL has 3 parts. And we can look at that here as well. Let me just look at my notes. So sorry about that, ladies and gents, I just had to deal with something. So we have the host name, so www, often the default website of the particular domain we might be seeing it. We will have the domain name, so for instance, Google, and we will have the suffix, i.e. .com. So suffixes represent certain types of websites. So .com refers to commercial organizations. It's not for things like, it's not a US version of anything. .com is commercial. You have .us occasionally. You might be seeing my email address is rjskinner@hotmail.co.uk. That's a UK version of commercial. .org refers to non-profits, .gov to governmental agencies, .edu for educational institutions. So for instance, .de refers to Germany, .uk to UK, and so on and so forth. So www, the default website that includes the home page of the particular domain, the domain name, for instance, Google, and then the .com is representing certain types of websites, i.e. the top level domain that they belong to. Domain names are registered through registrars, such as people like GoDaddy. Bear with me for 1 second. Okay, we'll carry on. That was my dog being delivered home, having been out of doggy daycare all day. I do apologize. IP addresses. The internet uses a numeric addressing approach computers can understand. The old style of address was IP version 4, which is actually running out of addresses and is slowly being replaced by IP version 6, which has many more possible addresses and would allow for assigning a unique address to every grain of sand in the world. The World Wide Web uses domain names as an addressing technique and then translate requests for domain names into the IP addresses. In addition to specifying the address of the web server, URLs typically also include the path to the requested resource, such as a particular page located in a particular directory. So IP addresses identify all computers and devices on the internet, allows messages to be routed to the proper destination. Okay, so there we go. An URL is easier to remember. Just remember, why do we go with URLs? Because they're easier to remember than an IP address. World Wide Web architecture, there are many different components that must all work together to make the internet and the World Wide Web seem like a seamless integrated whole. It takes several steps for a web page to be delivered. So the client requests the web page using the server's IP address. The server verifies it can send the web page and then breaks it into packets that stream to the client over the internet. The client reassembles the packets and requests a retransmission of any that are missing. Once the web page is reassembled, the web browser interprets the HTML and displays it. If any part of the web page is on a different server or in a different location, such as an image, the process begins again for that part of the page. So essentially that's what the internet and the World Wide Web, how the World Wide Web sits on the internet and leverages it to deliver access to a web page to be delivered. Related to this, we need to talk about extranets and intranets. So companies that want to share private data using the internet create intranets for internal use and extranets for use by themselves and partner organizations. These protected websites allow wide sharing, but with security to ensure data only reach the intended audience. So an intranet is a password protected website designed for sharing within the company. So for example, something like my wife Katie, when she wants to access patient data at the MD Anderson, they have an intranet set up so that she goes with that, so she can access very, very personal data in a secure function. And then an extranet, password protected website designed for sharing with select partners, would allow two organizations to do business on the internet together, for instance. And these are kind of typically protected by firewalls and the use of VPNs. And here we see them on the other page. So this top one, for instance, Katie will be working from home, my wife will be working from home, and she'll go over the internet using a VPN, and she'll go through a firewall, and then she'll have access to the patient data in the hospital. So a firewall secures proprietary information stored within the corporate local area network and or wide area network so that the information can be viewed only by authorized users. A VPN, a virtual private network, allows employees to securely connect to the company's intranet while on the road or working from home. so as we are all now at home. We're going to talk about firewalls and VPNs in the last chapter in the semester, in chapter 10. So an extranet, just a reminder, a private part of the internet that is cordoned off from ordinary users, enabling two firms to use the internet to do business together. Let's talk about components, IS infrastructure components. And the first one to talk about is data centers. And you'll remember from my first picture that I worked in data centers for many years. Companies often have large amounts of data that need to be managed on an ongoing basis. So if they set aside these dedicated centralized spaces for this, they can simplify their administration and also their operation. So things like management, repair, upgrade, security, all of these things benefit from a centralized approach to data management through the dedicated data center. Okay. Right, let's move to our next objective, which is the managerial issues associated with managing an organization's IS infrastructure. So these are some of the things, the specific challenges to consider when managing infrastructure. Let's look at some of these over the next few slides. Have I just repeated a slide? Yes, I have. Okay. So IT, information technology, the ever-changing churn of new technology, these IT cycles, they're shortening, aren't they? And as these IT cycles shorten, if you've done SAD, my systems analysis design class, you'll understand all about this systems development lifecycle and so on and so forth. As these IT cycles shorten, hardware that may still perform its intended function is becoming obsolete, and they will need to be replaced and they will need to be upgraded. Okay. Challenges shown on this slide include things like expanding consumption, expanding storage, increasing obsolescence, fluctuating demand, and diminishing space. All of these things need to be dealt with. Okay, all of these things need to be dealt with, and we're going to look at these further in today's class. Let's just take a touch back to the beginning of computing. It's always useful, I think, just to revisit where we've come from, because if you look forward and look back and learn from history, we can make sure we don't make the same mistakes and we can leverage the learning from before. When the computer revolution started to dawn back in the day, information systems for business and government organizations were paper-based. Right? Document repositories were rooms full of filing cabinets. Information was not widely shared, and when employees left a business, they took that knowledge with them. Okay. First back in the day, there's a typo in the book, by the way. The spelling of Zeus, which I don't know if you know is the Greek king of the gods, is in the book they've spelled it Z-U-S-E, and it's here spelled correctly on this slide, Z-E-U-S. So Zeus was the first computer back in the day, mechanical computer. The Leo, the first business commercial computer. I think we talked about it previously, 1951. Actually, I've got a bit of a tangent going on here. Here we go. Here's Dr. Ives, Dr. Blake Ives. Blake is a colleague of mine. You've probably seen him walking around the business school on the first floor where Starbucks used to be. That's where his office is. He's 6'8". He has one of the few people in the world to be awarded the AIS Leo Award. It's the top award in MIS for top professors. It's only been awarded 47 times. It is an outstanding award, and Blake is one of the very, very few people to be awarded it. And it's called the Leo after the first business computer in Lions Tea Rooms. There we go, an English thing that I used to go to. What were the generations of computing? Let's talk about the generation of computing, because again, it's important we just recognize the need to talk about it. There were some mechanical computers before, such as the Zeus Z1, but the real dawn of computing started with vacuum tubes and mainframe computers. Okay. Since then, we've seen a progression to transistors and transistor-based mainframes, and then to transistors on chips forming integrated circuits, which allowed for the economical development of the personal computer. Prices continue to drop, leading to low-cost PCs, followed by interpersonal computing, internet working, mobile computing, and the current era of social networking, big data, and the cloud. So here we have the technologies that defined the 6 generations of computing. One thing that's important to talk on, and I kind of talked about transistors, this is Moore's Law. Has anybody ever heard of Moore's Law? Maybe you have, I hope you have. Dr. Gordon Moore. Dr. Moore was a co-founder of Intel, actually. In 1964, he hypothesized that the number of transistors on a chip would double every 2 years, and he didn't put any time frame on this prediction. Although it's not exact, it has been a relatively accurate prediction, and it's become to be known as Moore's Law. So for instance, the Intel Core i7 Extreme CPU can complete hundreds of millions of operations every second. Given the technological and economic limitations today, gains in computer power are increasingly being realized by adding more and more computing cores that can perform tasks in parallel. Now, I think I did a check earlier on, 39.54 billion operations every second on AMD's Zen 2 on a commercially available microprocessor. 39.54, and I bet that's almost going to be out of date as well. I touched on IT cycles and obsolescence. We need to be really, really aware of it. Increases in capabilities in fast IT cycles is a blessing and a curse. There is a continuing cycle of hardware and application development that drives increased performance, but also rapid obsolescence. As each improves, it drives changes to the other, which in turn enables or drives changes to the first. Okay, so powerful computers enable new applications. New applications drive efficiencies. New applications make old hardware obsolete. Old hardware needs to be replaced, and away we go. Okay, it's both a blessing and a curse. If you jump off and you're not being updated with the latest technology, then you're going to get later left behind. So not only is the ITs and cycles and obsolescence is one of the defining component parts of our world, but also the need for big data. And big data has its boons and its challenges. So modern companies are seeing a tremendous influx of data driven by both compliance requirements and business intelligence needs. These new levels of data are driving infrastructure changes to support them, both in terms of storage capacity and processing capabilities. But it's a bit like a vicious circle, right? So you need to have the infrastructure changes to look after your new amounts of data from a storage capacity and the processing perspective, but then you've got to be able to have ever more bandwidth, which allows more data to be accessed and then analyzed and so on and so forth. It never stops. We're going to talk about these the roles of data in chapter 6, business intelligence, later on. So huge amounts of data leads to huge infrastructure capabilities, which allows for even more data, which allows for even more infrastructure capabilities, and so on and so forth. The big problem with this, of course, is with demand. Okay, is demand for data always going to be the same? Businesses often face large demand fluctuations on their infrastructure, building architectures that can handle peak loads, but which then are underutilized the majority of the time. Some experts believe that 70% of the installed IS capacity is only used 20% of the time. So one reason for this is that increasing IS infrastructure capacities takes time when equipment needs to be specified, purchased, installed, and configured. Just imagine the difference in need for a network for, say, Amazon in November and December as people are buying things at Christmas versus in the end of February, right? It's going to be chalk and cheese. It's going to be so different. And so the infrastructure you need to have in place for December and November is going to be very much greater than what you need in February. So how can you manage that so you don't have idle costs in your organization? Well, that's one problem that we need to think about. The other thing we need to think about is energy. So increasing energy needs. If you've ever been in a data center, you'll know that they're very, very cool because they give off so much energy that they need to be cooled to be able to function. I can remember one time in London, we don't have AC in London, ladies and gents, which is kind of a bit crazy. But in the summer, those few passing days when we have hot weather, we have no AC and things can get very, very hot indeed. And even when I was working at the bank, the European headquarters of Bank of America, they turned off all the AC that they had in the commercial buildings to send the power and AC down to the data center to make sure that the computers didn't overheat. So we were on the trading floor sweating ourselves away and all very wet and damp and horrible, just so that the computers could be kept cool, which I thought was the wrong priority, but there you go. Okay, so hardware draws power, which generates heat. Heat requires cooling, which requires more power, and so on and so forth. And large data centers, they have hundreds of racks, very noisy with all the AC trying to keep everything cool, giving off a lot of heat, and it's very, very inefficient, but that's just the way it is. So Google has invested many resources into developing more efficient data centers. They're trying to deal with this. So for example, there are modular data centers that use specially equipped shipping containers for housing servers so as to be able to maximize efficiency by optimizing airflow, cooling, and power transformation. In general, organizations have been looking for ways to better manage their IS infrastructure so as to enhance flexibility and agility while reducing costs. Okay? We think about people like Greta Thunberg, for instance. She is all about the need to keep an eye about this. Okay, we have to do a better job. We are now, there's a sense of responsibility that we need to be more cognizant about our power needs, our energy needs in the context of being cleaner, greener, and so on and so forth. So what can we do about this? What can we do? Well, maybe one way we can think about this is cloud computing. And that takes us to our, I think this is our final objective today. Describe cloud computing and other trends that can help an organization address IS infrastructure related challenges. We're going to look at managing the cloud, some of the advanced cloud applications, and touch on green computing. What is cloud computing? Okay, here we are. It's a way to allocate resources much like a utility sells power. So cloud computing is at its heart a different approach to allocating IS resources. The underlying concept is one of resource allocation as required, or on demand. Once this can occur, then it can be sold using a utility-like process. You need more access to infrastructure? There's your credit card, swipe it, instantaneously you have access to more infrastructure. You need to downsize? Same again, hand it back, no problem. So why is this possible? Why can we use cloud computing? Okay, because of the growth in internet bandwidth and advances in virtualization, ladies and gents. Okay, so we can now think about the infrastructure costs. If you're an accountant, you can move away from having infrastructure as a capital expenditure, and now it becomes an operational or operating expenditure. You now no longer have it on your books. It's not something you have to own. It's somebody else's problem. So cloud computing, okay, it's on demand as needed. You pay for what you use, you can grow, you can reallocate, you can hand back, you become very, very much more efficient than you have done before. So it allows ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interaction. Whoa, that's a bit of a mouthful. That is the actual definition of cloud computing. Let me read it to you again. Ubiquitous, convenient, on-demand, network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interaction. Okay. So why cloud computing? Why cloud computing? Here we have on the left-hand side, processing of data, storage of data, transmission of data. Cloud is almost like this metaphor for the internet. Organizations can use this utility computing model. Okay, so you can rent resources such as processing. They can have data storage or networking from an external provider on an as-needed basis, and they only pay for what they use. Okay, so it's efficient, it's cheap. You're using resources as efficiently and as effectively as you possibly can. So cloud computing allows for businesses to sell cloud resources through web interfaces. There's somebody at the front door. I'm going to stop recording again. 1 second, ladies and gents. I'm sorry about that. That was an Amazon delivery and my dog decided to bark at the Amazon deliverer. So what was I saying? Okay, yes, so cloud computing allows for businesses to sell cloud resources through web interfaces like other products, and it allows companies needing resources to buy them as needed, scaling up or scaling down as the business needs fluctuate. Cloud hosts have a pool of resources that are shared across many customers, with the varying demand levels balancing out across the pool. So, on-demand self-service, there we have. No need for lengthy negotiations. It's almost like a buffet style. You go up there and you help yourself what you need. Rapid elasticity, you can grow or shrink as you need. Broad network access, access anywhere. Fantastic. Resource pooling, which is the benefit to the cloud provider. You can get lots of people coming to access your cloud. You can pool them all together, and therefore you get better value for money for your cloud provision services. And a measured service. You only charge for what you use. There are different models of cloud computing. We have some here. So cloud resources can be sold in multiple ways. The cloud can host virtual machines on which the customer installs an operating system. In this way, it provides infrastructure, and that's infrastructure as a service, IaaS. A customer installs an operating system, all right? Second one, the cloud can also be used to host an environment in which programs can be executed. This is a platform approach, or PaaS. So the customer installs applications. And finally, the cloud may host pre-installed applications to which users just buy access. And this is software as a service approach, or SaaS. You also see things like XaaS, which is anything as a service, where they give you much more services on top of that. You have different types of cloud. You have public and private clouds. So companies are taking advantage of the many benefits of a cloud infrastructure by creating a private cloud for internal use within the organization. This allows for rapid allocation of resources across internal needs without the complications or concerns of outsourcing critical functions. Public clouds offer additional advantages, such as scalability and reliability, but may raise concerns about security and compliance. The thing we've got to think about is the privacy area. All right, so for the private cloud, you get rapid allocation of resources across internal needs without complications or concerns of outsourcing critical functions. You get to protect your own proprietary data in a way that you probably can't get the same level of security with an external provider. So there are many things to take into account when managing a cloud, whether public or private. Public clouds can present particular challenges because aspects of cloud management are outside the control of a business. So when considering a public cloud service, the business needs to make sure that it will meet the business's needs. Also needs to make sure it's a viable company, it's going to be around for a while, so it's suitable for investment and is appropriately priced. Security is a particular concern of many companies. I think I can't remember if I've told you about the high availability meeting I went to when I worked in Merrill Lynch back in the day. Flew into a meeting in New York from London, and I was there as a technical engineer, just talking about this high availability software. This is when you have two servers, one running hot, one running cold, which are identical to each other. So if one goes, the hot one goes, the cold one can take over straight away without being any downtime. And so we had 5 or 6 people coming in, different companies with their solution software, wanting us to buy it. And we actually went with the second best. And the first best was brilliant, miles better than anybody other else's. But we didn't go for it because we didn't think they were going to be around in 3 to 5 years' time. The viability of the strategic direction was not in place. And so we couldn't take forward our relationship forward with them because it just didn't make sense to do so. So let's look at some advanced cloud applications. The first one I'm going to touch on is this thing called SOA, or Service-Oriented Architecture. So to achieve greater flexibility and agility, organizations have sought to move away from deploying large kind of monolithic applications in favor of this thing called an SOA, or Service-Oriented Architecture. So by breaking down business processes into individual services, organizations can more swiftly react to changing business needs. So SOAs are hosted and deployed in the cloud, eliminating the need for an organization to reinvent the wheel. However, integration of various services can be extremely complex and can be well beyond the means of small enterprises. Okay, so instead of let's give me an example. Think about the next time you do an oil change on your car, right? You probably aren't an expert on it. You can't be an expert in everything. So it's probably going to be more effective to have someone change the oil for your car for you. So what are your choices? You can go to a garage, you can go to a dealership or you can speak to a knowledgeable friend, all right? They can all have what it takes to change your oil in your car. You don't care, really. All that is important to you is that the service is provided at the expected level of quality and cost. You don't care what tools are used. And that's essentially what you're doing with a service-oriented architecture. All you do want is the services provided, right? As a client, that's all you want. You want to be able to provide these services to your clients. And this is what an SOA approach is all about. The other thing we talked about earlier on is this thing called grid computing. Really complicated problems, weather forecasting when the hurricanes are coming in. This is all using big supercomputers. Here's this one's called Titan. The Titan supercomputer can perform more than 20,000 trillion calculations per second. So people like Toyota, for instance, simulate car crashes as part of the design process. Oak Ridge National Lab doing climate change. Very expensive, not always used all the time. Typically seen for research and development. It's just very, very expensive. This is the one I use. This is the UT's one. I'm helping my wife do some research on multiple permutations about how different types of immune cells react to different treatment scenarios. We're in billions and billions of permutations. MD Anderson, if you didn't know, is a part of University of Texas, and this is their University of Texas supercomputer. Pretty darn powerful. What does it say there? How's it got? 398,000 cores from a CPUs. Laptop probably has 4 to 6. Yeah, it's pretty scary actually having access to it and doing all the things that you need to do. Something else I want to touch on, which you may have not come across, but is very cool, and one of my favorite things, is grid computing. The problem with supercomputers, right, they're dedicated, they're integrated computers, they're great for solving complex problems. They are incredibly expensive. An alternative is this thing called grid computing. So some problems can be decomposed into small sections, and these can be processed across a grid of many microcomputers, with the end results being integrated back together. These grids can solve very demanding problems, formerly solvable only by supercomputers, and can be comprised of regular desktop PCs. These desktop computers can be configured to contribute to the grid when they have idle excess capacity, which is very often the case when users are performing simple tasks such as word processing. Okay, so do you remember this picture? So back in the day when I worked at Merrill Lynch, we had a trading floor which is this size. You know, you've got 1,000 people on the trading floor. Crazy. Trading hours, well, the first traders typically come in at about 6:30 in the morning, and the last traders, main bunch of the traders, probably leave at about 5:30, 6 o'clock at night. So Monday to Friday, you're only using 12 hours of the day. So you're using 60 hours out of the whole week. Okay, it's not very many. Out of 168 hours in the week, you're using 60. So you've got 100 plus hours in the week where all these quite powerful workstations are not being used. So back in the day, has anybody ever heard of SETI, the Search for Extraterrestrial Intelligence? So SETI, me and my friends back, this must have been about 20 years ago when I was doing desktop support, decided that we were going to help with SETI because we think SETI is great. And this is, I got into quite a lot of trouble about this, ladies and gentlemen. I don't know what I'm telling you. Anyway, we set up a little grid of all the workstations not being used by the traders to help us compute power for SETI, so that they could just do all the calculations that they needed to do for all the data that they were getting in, and so on and so forth. And it was the first example in our bank of grid computing. And we got told off big time. But we got away with it because they loved the idea of what we were doing, and then they adopted it so that when they were doing their processing and analysis processing overnight when the traders weren't there. They used the grid setup to leverage the workstation power to help them do all their computations more quickly. So there was an upside, but it was quite funny. Anyway, grid computing. I like grid computing. I'm a big fan of it. What else? Content delivery networks. They store copies of content closer to the end user. So larger geographical distances can lead to longer content transmission time. Okay, content delivery networks involve multiple servers at various locations, the user request being routed to the closest server. Okay, so streaming media, for instance, you may have it all located at different servers, and you will access the one which is closest to you. Another one, this is all what this is all about. What we got? Oh yes, the convergence of computing and telecommunications. So modern information system infrastructures are now servicing many an organization's communication and telecommunication needs. Telephone services being provided through things like voice over IP, things like that. IS infrastructures support email, instant messaging, and video conferencing using either desktop or dedicated installations. So things like Skype, for instance. And we're going to talk about this, about video conferencing and voice over IP in chapter 5. The last thing I just want to touch on, because we do have to be aware of it, and Greta Thunberg is one of the reasons why we do, is green computing. So green computing is all about lowering the bills of power, increasing our reputation for being responsible players in the global economy, and putting forward a culture of green thinking. It has multiple drivers, economic and cultural. So as I say, spiraling power pools dictate practices to increase efficiency and reduce waste, while implementing environmentally sound practices can burnish a company's reputation and contribute to an attractive work culture. There are multiple opportunities to implement green computing, ranging from increased efficiency through cloud computing and server virtualization, where companies can take many physical servers and combine them so they run on a single larger and more efficient server, each in its own virtual space. Companies can implement power management software to minimize the power consumption of computers when they aren't in use, such as computers left on overnight, such as Professor Skinner did. Reducing printing can be significant. The average office worker prints more than a tree's worth of paper every year. Finally, responsibly retiring and recycling obsolete or unused equipment can mitigate the end-of-life environmental impacts. So green computing, green generally, is a hot topic because of Miss Thunberg, who I have huge admiration for, I must say. I think she's wonderful. Right, a lot going on there. I do apologize for the stops and starts. I know they appear seamless to you because they happen in real time and I just paused recording. Mostly to do with my dog coming back from doggy daycare and Amazon package being delivered, which I don't know what it is. I'm going to open up very shortly. It's very exciting. Your assignments. So groups 4 and 2 will do case 1, a catalyst for innovation, AWS, on page 135, answers questions 347 and 348. Group 1 and 5, case 2, the dark web. Oh, that's a good one, on page 136. And group 6 and 3, ethical dilemma, putting people's lives online, on page 97. I hope you've enjoyed the class. It's quite a lot going on there. One of the more busy chapters. If you've got any questions, do let me know. For this class, I will, of course, next time be in the classroom ready to have any questions you may have. Just come in, dial into the class, and I'll be there and happy to help in any way I can. Alrighty, well, thank you so much. Please continue to take care of yourself. And if you've got any questions, please just reach out to me. This is Dr. Skinner signing off. Take care, bye-bye.